everyone, my name is Shaktivel Murugan. I am an assistant professor in the Department of Mechanical Engineering. Today I am going to give a presentation in the topic of reverse engineering in automotive products. So mostly reverse engineering can be applicable in most of the domains. So in specifically reverse engineering, in this video we are going to discuss more about how reverse engineering is applicable only in automotive sectors. So other than this domain, reverse engineering can be applicable in aerospace, can be applicable in biomedical applications, and also it can be applicable in most of the metrology and quality inspection sectors and etc. So next, before going to discuss about the applications of reverse engineering, so before going that, let's give a small introduction about what is reverse engineering. Reverse engineering is defined as the process of obtaining a CAD geometry from a 3D points acquired from hardware device known as 3D scanning. Using 3D scanning, it is a stereographic camera setups, so it captures the data points throughout the entire component in a 360 degree. So based on this, the 3D data points can be captured in a format of point clouds. That point cloud data can be processed further and can be used as a recreation of this 3D complex 3D geometric modeling. So that is what the reverse engineering. And here first, before in the traditional 3D solid modeling, drawing is mandate, but in this reverse engineering we are going to get the 3D objects only from a 3-dimensional object. So physical object is mandate. From this physical object we are going to scan the data points through a 3D scanner, and from this hardware setup we are going to collect the reverse engineering bridge, that is the 3D point cloud data can be collected together and can be further mapped with some triangulation format, that is triangulation, because every 3 points should be connected using a triangle. That triangle will be formed as a patch, surface patches. That surface patches form as solid objects. So there's surface patches will be converted to CAD modeling. That particular CAD modeling is redefined and it can be revised, and it is filtered by using some wrong data, like some of the surface may be not formed correctly. So those types of surface patches and surface corrections and smoothing corrections should be done in post-processing setup, and finally we made a CAD model. This CAD model is used further for manufacturing cycles in any of the domain. So this is reverse engineering. So the uses of reverse engineering is applicable in many aspects. The first one is, if the original manufacturing design is no longer exist, or it may be deleted, or it may be used by some other industries, and our own industries want to recreate those designs. So in this particular aspects we have to use this reverse engineering. And if the original manufacturing has no longer exist, because if you want to recreate the model of an engineering component which was used in the earlier days around in the World War I or World War II situations, those components if we want to recreate, so in this aspects we need to go for reverse engineering. And the original product of the documentation has been lost or deleted, and the inspection or quality comparing to the fabricated product, because if we want to make a quality checking of an actual component, so we need superimposition technique. For this we need an actual CAD component and a reverse engineering component. When we superimpose each other, then we can get that standard deviations in the measurements. So easily you can check how quality we can manufacturing this entire component. So it is used for quality inspection process like that, and for analyzing good and bad features around the competitors market and exploring the new avenues to improve the product performance. And for these concepts we have to use reverse engineering. And before going to in this video, we are going to discuss only about the automotive sectors. So in this automotive sectors, why we are using reverse engineering only specifically for the automotive sector is discussed now. So the particularly in automotive sectors, most of the components are formed by free-form structures. Free-form means it is a structure which cannot be created using parametric modeling. The surfaces may be in a very smoothened manner. All the smooth surfaces can be connected by Bezier curves or B-spline curves, and the curves will be interconnected to form a surfaces, that is Bezier or B-spline surfaces, and sometimes nerves, non-uniform rational B-splines, and these surfaces may form the continuities like C1, C0 continuities. Based on these continuities, some solid models has been recreated. So mostly if you take any automotive components, the surfaces, it is the complex surfaces has been found in the front bonnet, front dome, and in the automotive rears and back sides of the automotive sectors and the side coverage. Entire automotive is completely full of free-form structures. And to overcome those obstacles, several data exchanges and data integrity has been happened. So data exchanges means To recreate an automotive component, one data format is not sufficient. We need to create a data and 3D model in one particular software, and we have to go for CNC or CNC machining in some other format, and we have to go for CAE, computed analysis, in some other software. Several softwares we need to use, and based on this output, that final component may be fabricated. So several data concepts may be integrated. So for this we need to handle several n number of data concepts. So for this, using this reverse engineering, it will be quite easy to achieve all those types of data integrity and data formats. So whenever if you are go for some smooth profile, so the complexity of the design will be increased. So it should not be in a very free, it should not be a model using a parametric modeling. So whenever if the complexity increases, so the time to recreate using surface modeling or some other tools will be take some time consuming process. So reverse engineering is the only process to make the entire designs and to be captured in a very short span of time. So therefore we have to seek the help from this reverse engineering aspects and we have to correct problems arising from discrepancies from the CAD master files and the productions files, and we have to compare the CAD files and the productive actual files. We have to get the both data and superimpose together, and we have to represent it in a form of some color deviation maps. Use these color deviation maps is helpful in tolerance deviation analysis, and which is useful to create an high accuracy products. So that's why this reverse engineering will be very useful, and also some other performance improvements like CAE, CFD. We have to get some CAD model of the existing files. Therefore this reverse engineering is most important. So based on all these reasons, this reverse engineering will be very useful to do all these tasks, particularly which is very applicable and useful for automotive sectors. And before going to start, we will explain you about the process flow of this reverse engineering process in automotive sector. First it will be start with some small scale clay modeling. So whenever if you are go for some other component modifications, initially engineers will do using some clay model. So after making the clay model, they have to capture it by using some data scan, that is a 3D scanning. So using this data acquisition device, particularly the 3D scanning, they have to capture all those data points and convert those into some initial CAD modeling software through the reverse engineering software. So based upon this CAD modeling, so mostly this types of modeling will be done through polygonization or NURBS. NURBS is non-uniform rational B-splines. So the polygonization is nothing but the patches of every segments. The collection of all the point cloud data will be connected together by use of B-splines. So B-splines and NURBS will be connected together and it will form a surface modeling. So several surfaces encloses together to make a solid modeling. Based upon this concept will be done through a proper reverse engineering software, and we have to get a full scale model. So this full scale model will be used in CAD CAE and CAD software packages. Once if we have completed the full scan model, then we have to scan it and we have to refine this entire design using some noise reduction, some missed data particle patchings and some other patching works and some other refinements works. Based on this, all these redesigning works, then we have to get the final model. Once if the final model is done, then we have to use this final model for some other CAM or CAE or CFD operations. So this is the work flow of automotive design. These are the components that will be used in this workflow. And this is an case study examples how one of the automotive component. In this slides I will given a small automotive component example as a piston. So engine piston is a small gas component based upon some other data acquisition device. So they have captured all the data points in this piston using some, it is converted to a point cloud data based upon the hardware devices that is used. So here it is the collection of thousands of points. This thousands of points will be converted to polygonal mesh. So that is known as meshing concept. So the polygonal mesh will be converted to CAD modeling based upon the connectivity by using of NURBS. So NURBS is non-uniform rational B-spline curves. So these polygonal curves will be connected to NURBS. So using some smooth curves, the surface modeling will be done. Once the surface modeling will be done, then it will be patched together and it forms a solid model. So initial CAD model is defined. Once the initial CAD model is defined, we have to refine it and we have to go for some meshed model. This meshed model will be used in most of the CFD and CAE operations. So you can use it for CFD, CAE operations, and we have to use for finite element analysis for the evaluation of how much of stress act on it, how much of heat temperatures affect by using this particular component, how much deformation is attained. Based on this, we will get the data of the finite element analysis, and once the CAE model is done, we have to get some design modifications, and the final CAD model will be done, which is usually finally we can attain the optimized design. Once this optimized CAD model will be used for final optimized manufacturing process using some traditional conventional non-conventional manufacturing or additive manufacturing process. These are the process flow of the automotive sectors. Okay. So right now we have given about the most of the sectors. So here I will share you some of the case studies which will be useful how this reverse engineering is used in automotive sectors. The first case study is General Motors virtual NASCAR SB2 engine block. So it is one of the case study where the objective of this case study is they have to use reverse engineering system to capture a data of a classical traditional model car. So in that traditional model car, the name of that old engine, that is SB2 engine. So usually the SB2 engines emerging in the time of World War I. So 1920s, at that time this car model came. So several features are that it is having high horsepower, high torque transmissions, etc. There are some of the most of the advanced features are there. But what happened is after certain existing affairs, so the mold for using the production of this engine block has been damaged, and it is some other components it will be missed. So engineers want to recreate this SB2 engine block, so particularly with the help of General Motors. So what they have do is they will seek the help of reverse engineering. So the 3D molds and the cores again they have reconstructed, so which was missed in 1950s. So also its entire SB2 engine block they didn't have any 2D drawings or some other 3D model drawings existing. There is no drawing components is available. So they have to recreate this entire one by using this reverse engineering techniques. But one thing while doing these types of projects, what they have to focus, they never compromise on quality and accuracy of this component. Even they have to focus on very minute tolerance. So this engine block should be manufactured as much accurate as much as possible. So they need the casting tolerance of plus or minus 0.03 inches. So if you have manufactured this component in this particular tolerance, then it can be perform high performance. Okay. So at the same time we have to capture the entire cavities or datas. So it should be poured into the sand core. We have to make it bosses for the block casting process. So several casting components has been worn out and it will be damaged. So what happened is using those damaged components they pour some urethane molds and we will get some soft models. Soft models is it will be some flexible models. Those flexible models is reverse engineer, and based on the CAD model they again recreate that molds which will be useful for the production of this engine cast models. So based on this is the traditional SB2 Chevrolet engine block. So these are the worn out components of the molds which is used for manufacturing this engine block. So these two components has been reverse engineered using several 3D scanning techniques. So engineers 3D scan all these entire datas and they have to correct this entire scan datas and they have to get the actual CAD model of this engine block by using several refinement process. So it will take 4 to 6 months time to grab all these point cloud datas and refinement of these datas, and once the refinements they have to verify it, and based on the tolerance of 0.03 inches they have to again rework it, and once the final optimized design has been confirmed they have manufactured this component using the traditional CNC machines. So likewise they have to successfully completed this General Motors this SB2 engine block. So this is one of the most important renovations in the reverse engineering history in the field of automotive sectors. And another case study I want to explain is this Ferrari's 550 Marinos. So it is a sports car. So usually in the year of 1916s, while entering into the track of several sports cars, there is a heavy competitions. So each and every car finishing the race in a very minute variations in seconds. So it is one of the 24 hours duration race course, track. So in this track, the Ferrari 550 Marino is a car which is participated in this particular one. So engineers what they decided is they have to win in this particular racings. So for that they mainly focused on the problem that is arised from the tail wing. So the rear wing or the tail wing. So in this they have to modify the design. So for that they have to first redesign the entire car model in a 3D CAD solid model. So first for that they have to reverse engineering this entire car model. Why they have to reverse engineer the entire car model? Because our objective is to manufacturing the rear wing or tail wing. But in case if you want to redesign or modify the rear wing, they have to get the data of the entire car model for doing the CFD analysis. So once if we have performed the CFD, so along with this the fitment of this tail wing, so if the performance will be improved, they have to iterate several designs. For example, they have to collect all those data of this entire car model, and they have to do the CFD analysis for the entire car model, and they have to change or design modifying the tail wing. So several hundreds of designs has been redesigned. So based on this several iterative designs, one best design of the tail wing has been collected based upon the performance of that entire car body. So that tail wing has been again manufactured by using some traditional CNC machines. So that components will be fitted into the real model Ferrari Moreno speeds. So based upon the implementation of this particular tail wing, the performance of this entire car will be improved. So that makes this Ferrari car to win in those 24 hours racetrack in a very short span of time. So that is what the success of this particular one. So here this is the Ferrari Moreno's car model. So they have the engineers redesign this entire car. So once the redesign has been done, they perform this CFD analysis, computational fluid dynamics. Once they have made this computational fluid dynamics, they have to redesign this entire tail wing. So this is the tail wing. So they have to recreate several iterative designs of the tail wing, and once if they have redesigned this tail wing, they again perform the CFD. So based upon the hundreds of results, they have collected the best results. In that best results, they have get the parameters of the design of this tail wing. That design is made further iterated to get an optimized tail wing designs. That tail wing design is manufactured using these CNCs. Once if we have modified this tail wing design, this car is able to finish this entire lap in a very short span of time. So that's it. And these are the major case studies. Again, I will confirm you this automotive sectors used reverse engineering for quality enhancement. So this is one of the automotive component. So in this automotive component, this CAD model, this is the actual CAD model that we are having. This is the scanned model which is done through reverse engineering. We have to superimpose and we have to get the color maps. Using this color map, we have to get some deviations in the tolerance. When the color is high, that is red color indicates more tolerance deviations, and green color indicates no tolerance deviations. So in this color maps, if you are observed the more tolerance deviations, then we have to rework or redesign using this CAD model. Then we have to send for the CNC operations. Then it is a very easy task to enhance the quality of this entire design. And similarly, some of the automotive components they are using for quality enhancements. This is an example of a automotive car door that they are using this reverse engineering techniques for quality enhancement. And finally, using this, I will conclude my today's topic. So the convergence of this digital prototype and the physical model, particularly in automotive sectors. Why we are using 3D automotive sectors using this reverse engineering is particularly this automotive sectors useful in ergonomics design, because mostly if you have selected any automotive design, that a particular car model is have several freeform shapes. If you have taken the automotive seats, it's completely designed by using the ergonomic designs. So whenever if you give importance to ergonomics, so more curves should be done, that is freeforms will be done. That will be very easy to recreate by using this reverse engineering techniques. And the aesthetic appearance. So only in the focus of aesthetics, we have to design an automotive sectors which using several smooth surfaces and curves, which is helpful to recreate using this reverse engineering. And the aerodynamics. So we have to perform some CFD analysis for the performance improvement and the air resistance and drag analysis. For this, we need some CAD model. Reverse engineering will be helpful to using this analysis. And the flow dynamics, mostly in an engine blocks. So the inlet and outlet, the flow velocities and the pressure improvements. So we have to do some flow analysis using the same CFD softwares. For this also we need this types of CAD model. And the time own components. If the time own or damaged components occurs, it is very tough to recreate using the traditional parametric modeling designs. So therefore the reverse engineering will be helpful, and statistical analysis will be performed to get the missed data, and it will be very useful to recreate those components, which will be very useful for an automotive sectors, which is an commercially successful about this competitive world. So if industry is focusing on this reverse engineering to recreate the design in a very short span of time, really that designs will commercially hit a major success. It will reach a huge welcome by the customers in that entire market sectors, and that's why it is useful to implement those reverse engineering designs easily in a short span of time to enhance the design in a very accurate manner and also with a reliable manner. So that's it. So here now I conclude and summarize my speech. So in this sessions I have taken the sessions about the reverse engineering and its scope, how it is applied in automotive sectors. So how the automotive sectors using the support from the reverse engineering and how they are remanufactured in this entire component in a short span of time with high accuracies and high tolerance with less tolerance deviations. So how it easily reaches the customers and how using this reverse engineering how the performance has been improved, always discussed in this sessions. So thanks for the wonderful opportunities and thank you all.